Hi everyone, I'm Harry Rubin-Falcone. I'm a PhD student at the University of Michigan in Computer Science and Engineering, working with Jenna Wiens. Our work here is focused on tackling the KDH blood glucose prediction challenge using deep residual forecasting. Diabetes affects millions of people worldwide, with a prevalence greater than 10% of adults in some countries. It is a condition in which the body produces little or no insulin, or is unable to use the insulin that it produces, which results in poor regulation of blood glucose, or sugar in the blood. Blood glucose management is important to the overall health of an individual, since high blood glucose values, or hyperglycemia, characterized as values above 180, can lead to long-term adverse outcomes like kidney damage and cardiovascular disease, while low blood glucose values, or periods of hypoglycemia, characterized as values below 70, can lead to coma and even death. To help managing blood glucose, individuals with type 1 diabetes often wear continuous glucose monitors. These devices regularly measure and record blood glucose values in real time. Equipped with an early warning system based on predicted future blood glucose values, these devices could further help individuals prevent periods of hyper or hypoglycemia. To this end, the task of predicting blood glucose values, or forecasting, is an important task to the diabetes research community. In fact, the KDH blood glucose level prediction challenge aims to improve overall blood glucose forecasting. The challenge considers 6 adults with type 1 diabetes. Longitudinal data pertaining to blood glucose measurements, insulin administered, and other contextual variables like carbohydrates ingested were collected from wearables over the course of 8 weeks. As part of the challenge, researchers were tasked with building models to forecast blood glucose values 30 and 60 minutes into the future for each individual. Our proposed approach is based on deep residual forecasting. We were motivated by the strong performance of Oreshkin et al.'s proposed architecture on the M4 competition dataset, a benchmark forecasting challenge that considered time series like stock prices and tourism amount, but did not explore forecasting tasks involving physiological signals like blood glucose forecasting. The main idea behind deep residual forecasting is to predict a signal gradually in stages. An input signal is given to a subnetwork composed of fully connected layers, which outputs a forecast over some horizon, for example the next 30 minutes, and a backcast or a reconstruction of the input. The backcast is subtracted from the input to generate a residual. This residual is input into a different subnetwork, which in turn outputs a new forecast and backcast, from which a new residual is generated. These residuals are computed iteratively for some fixed number of iterations until finally the forecasts from all steps are summed to give a final prediction. In this way, the model learns to reconstruct the signal gradually while making predictions along the way. We build on this approach in 4 ways. First, we explicitly account for temporal relationships by replacing the fully connected networks with recurrent neural networks. Second, we consider a multivariate input, including variables like time of day and insulin delivered, which provide important context. Third, we add additional terms to our loss function with the goal of supervising the model so that the forecasts are more directed, the backcasts are more accurate, and that the backcasts are also more incremental in nature. We also experiment with using a large dataset to pre-train our model. Combined, these changes result in improved performance across the 6 individuals. We achieve a 30-minute root mean square error of 18.22, nearly 3 points lower than our baseline model, which is the model originally implemented by Oreshkin et al. We will now go into more detail on our baseline architecture and then on our modifications and results. The network consists of multiple stacked blocks, each containing a stack of fully connected neural networks. Each block outputs a forecast, which predicts the next time points, and a backcast, which is a reconstruction of the block's input. The reconstruction is subtracted from the block's input. This residual gets input to the next block. Each block's forecast is summed for the final output. In this way, the model learns to reconstruct its input and predict future values incrementally. We modify this baseline architecture in 3 ways. We will now go into more detail on our modifications to this architecture. Here's an overview. First, we update the block structure to better deal with temporal data. The original architecture uses a fully connected stack in each block. This design cannot account for temporal dependencies since each input value is equivalent mathematically. We therefore used bidirectional STMs, a powerful RNN, in our block design. This enforces a sequential prior on the data so that the model must learn temporal dependencies, which results in predictions that better capture trends in the data. Additional channels also make adding auxiliary variables more straightforward. We use the multiple channels of each RNN to add context variables to the model. The variables added are bolus amount, carbohydrate input, sine and cosine of time of day, and fingerstick glucose. These variables were all found to be helpful during tuning. Due to the sparse nature of some of these variables, we backcast only on blood glucose and input the raw values of each other signal directly into each block. We hypothesized that forcing the model to reconstruct such sparse inputs would hurt performance. Our architecture has multiple opportunities for supervision, which we could take advantage of to ensure that the architecture is performing as we would expect. A standard model's loss is only a measure of the error of the prediction. We add loss terms to supervise the model. One desired characteristic of our model includes that each block's forecast contributes towards a correct prediction, which we enforce by adding additional loss terms for the error between the actual data to be predicted and a running sum of the predictions at each block, rather than only including the final predictions. We attempt to ensure that each block reconstructs its input accurately by adding a loss term with the error between its input glucose and backcast result. And we encourage the blocks to learn to reconstruct the input signal gradually, rather than all at once in a single block, by penalizing low-value backcasts. In order to ensure that each block's forecast moves the sum towards the correct overall forecast, we calculate loss using the error of the sum of block predictions with respect to the actual signal y after each block. We scale each term so that later blocks are weighted more heavily, since later blocks should be much closer to the final forecast than earlier ones. We use mean squared error as our loss function, here depicted as L. In order to ensure that each block is accurately reconstructing its input, we calculate MSE between each block's input glucose value and backcast over all n blocks. We weigh later blocks more heavily. This is motivated by the hope that the signal has been deconstructed by the time it reaches later blocks, so later blocks should have more faithful backcasts. It is possible that the model can learn to predict the entire signal at one block. However, the purpose of deep residual forecasting is to learn the signal gradually. In order to ensure that each block contributes to the signal, we penalize blocks with small reconstruction outputs by adding the inverse of their norm to the loss. We weigh earlier blocks more heavily to allow later blocks to have smaller outputs as the residual gets smaller. Finally, we initialize our model by pre-training on a much larger dataset comprised of blood glucose from individuals who uploaded their data to the TidePool database. For all analyses, we build a model using data from all 6 participants, and then fine-tune this global model to each participant. We use our pre-trained model to initialize the global model. Some key implementation details are as follows. Rather than interpolating, we set all missing blood glucose values to 0 and add an additional variable set to 1 when blood glucose is missing and 0 otherwise to the model. This allows the model to learn when blood glucose isn't being recorded, which can be valuable context. We run a total of 6 models, each with a different input length. We use lengths 12 to 42 in multiples of 6. We then output the median of this ensemble as our final prediction. As discussed in Oreshkin et al., this adds a multi-scale aspect to our approach. When added incrementally, we see that each of our method updates contribute to improved performance, although to varying degrees. Shown here is the root mean squared error for a 30-minute prediction horizon across 6 participants. The orange line indicates the median across all participants, while the blue line is the average. Our baseline, which is the model implemented by Oreshkin et al., achieves an average value of 21.2. Using an LSTM in the block structure improves performance to 20.1. This was likely due to the network's superior ability to model time series data compared to the fully connected layers used in the baseline. Added variables also offer substantial improvement, decreasing rMSE to 18.94. We found that including these variables increased performance more using an RNN block structure when compared to including them with a fully connected block structure. This was likely due to an RNN's multiple channel architecture. As expected, backcasting on just blood glucose improved performance more than backcasting on all variables. The additional loss terms were only minimally helpful, with an rMSE of 18.87. This was surprising since they were quite beneficial in the tuning stages of model development. Tuning was carried out on the 2018 competition data, on which we observed a smaller improvement from the additional variables. Perhaps then, the additional supervision terms are best suited for data where context is missing from the available data. We found that pre-training on the large dataset improved performance, indicating that the model benefited from having many more patients' data available. This highlights the importance of public availability of large data sets for future studies. Our final root mean squared error was 18.22. In short, we find that deep residual forecasting performs well on blood glucose data, and that using RNN blocks, added variables including bolus insulin and carbohydrate input, additional supervision, and pre-training on a large data set all improve performance. Our full paper and code are available at the GitLab link shown here, and I can be reached at hrf@umich.edu. Thank you for your time and attention.